All right, this balloon, what shape would you call it? A sphere. Thank you, Hannah. You win. All right, now, there's air in here, right? Mathematically, how do you represent air inside something? Volume, very good. Okay, so if you wanted to do the volume mathematically, how would you find it? Do you know the formula? Oh my goodness. Not through a sphere. It's 4/3 pi r cubed. All right, so how would I find the r of this? I measure like straight across somehow, maybe, and divide by 2? Okay. So there's a certain volume in here, there's a certain radius, right? Okay, I'm going to let some of the air out. I'm going to let it out pretty slowly. Okay? All right. Now. All right. So what besides the volume, what has changed?
The radius.
The radius. Okay? So those are, now, the radius is changing. I said I let it out slowly. I can also put it back in, right? Okay, now I'm going to do it real fast. All right. Now, the rate that volume came out is a derivative. There's also the radius is changing at a certain rate. That's a derivative of a radius. Okay? So these are all, related rates. All right. Okay. All right. So this is all implicit derivatives. Now, if I would have to pick out a weakest area of derivatives on that quest, it would be implicit. So we got to be careful. But anyway, related rate problems involve finding the rate at which a quantity is changing, which is a derivative, by relating that quantity to other quantities whose rates of change are known. Okay? The rate of change here is usually with respect to time. Okay? In my experience, it's always with respect to time or calc time. Okay? So you can change it usually to always for calc time. All right, so there are directions for what we're going to do. We're going to take an example, and then we'll come back to the directions. So next page, we are going to look at this cone. All right? This is a cone, party hats. What is the volume of a cone again? That wasn't the sphere one that we just talked about. 4/3. No, that was the sphere. 1/3. 1/3. Squared times h. Good job. Okay, now, there are these, you're going to have to know these, girls, so if you don't know them, you just have to start a list and then put them on your whatever. Okay, now, just to kind of get ready for the related rates, we're not going to start any kind of problem because we don't have anything. We are going to just figure out how dV, dt, dr, dt, and dh, dt are going to show up in this. Okay, so the dV, dt means what? Derivative of the velocity. In this case, it is volume. Okay? Derivative of the volume with respect to time. So time is the variable. Okay? Time is the variable here. Time is the variable here. Okay? You are going to solve this with one variable. Now, we have several variables going on, so this is how we're going to do it. We're going to take the volume equation of a cone. The cone one comes up a lot, sphere one not so much. Okay, and we're going to take the derivative of each side. Okay? Now, because we're doing a derivative with respect to time, it's all implicit differentiation. Because there's no t involved, right? All right, so dV dt, that's the easy part. Done. Remember, it's 1, and then you do this, the derivative is 1, and then you do dV dt because you're not dealing with v deal. Okay, now 1/3 in pi is a constant, so I'm just going to pull that around. And how are we going to find the derivative of r squared times h. Wonderful. Very good. Okay. So, product for here. All right, Catherine, you want to start it for me?
Sure. R derivative of R squared.
Is, okay. All right. We can do that. Derivative of r squared times h.
Plus R squared times H.
Okay. Are you all still needing to write that?
Just one.
Okay. There's no shame in that. If you want to be honestly. Okay. Now remember, we're doing with respect to time. Okay. So what would you find? Well, how would you find the derivative of r squared with respect to time? What's the derivative of r squared if we weren't talking about implicit differentiation? 2r. So what do we have to add on to that? We'll really multiply on d r dt. dt is going to be the bottom every time. Yep. H plus r squared times dt. Okay. All right, we're done. That's all we're doing. We're not really solving anything. We were just finding an equation that represents. Okay, now what will happen next is that we will start plugging in. And we will either find ddt or find drdt or find dHdt. And then we'll have to give us some of these other values. Okay? All right, so let's try one and we will. Oh, sorry. Now the problems get harder as we go through the notes. So, yes. Ready? Okay. So we will do this problem. I'm going to put it on 2 pages. So that's why I got switched around so that you can see the directions. All right. Okay. So here we go. Problem 1, a golfer hits a ball into the lake in front of the green. Okay, there's your ball. As it enters the water, it causes ripples in the form of concentric circles. So ripple, circle, 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 right? That begin at the point of impact at a steady rate of 3/4 feet per second. I'm identifying that as a rate because I know that's a derivative, all right? What is the rate of change of the area of the outermost ripple when its radius is 3 feet? Okay, so we are talking about identify the known rates of change and the rate of change that is to be found and write an equation. These kind of have to go together because you can't really determine a variable until you say, oh wait, I don't need that, because you wouldn't start with like circumference because it doesn't mention. So what are we talking about? Area of what shape? All right, and what's the formula for area of a circle? R squared. Okay. Yeah, so like the subscript. Okay, that's a circle. All right. Now, let's figure out what we know here. This is step 2 technically, but 2 and 1 gotta be together. Okay, so it looks like rate of 3/4 feet per second. What is changing? Area or radius? Okay. But if you look, it says what is the rate of change of area? So we don't know that, right? So dA dt is unknown. Okay. So this has got to be, the 3/4 has got to be what? So what would you call it? It's the rate of change of the radius with respect to time. dr dt. Okay. Now another thing I use for figuring out, because sometimes it is hard to figure out what is what, I look at the units. If this is not feet squared per second, it's not a rate of area changing, right? Okay, so pay attention to the units, they'll help you. All right, so what else are we looking, or what else do we know besides these 3 things? At this moment, and remember, our derivative is an instantaneous rate. So what is the moment when we know, what do we know? Find the rate of change. Remember the balloon. When, what do we know? R equals 3. Okay. So we know this. We're looking for this at that moment. Okay? We know this. We're looking for this at this moment. Okay. So here's what we're going to do is step 1. And number 3 says differentiate with respect to time. All right, here we go. What is the derivative of A with respect to time? I just said it. dA dt. Okay, pi is a constant. What's the derivative of R squared with respect to time? And
2R dr dt.
very good. Okay,
Is that step 3?
that is step 2. 3, yes, differentiate. Okay. All right, now the next thing, once you have it differentiating, you can plug in the known rates of change. Okay, I think when you get your quest back, you'll be like, I've made a comment on some of those implicit that you could have plugged in a lot sooner. A lot of you spent a whole lot of time doing some algebra, and then you plugged in, it was all pretty. Remember we talked about that? You don't have to. All you really need is the derivative. You can plug it in way sooner than some of you did. And some of you, it was fine, and some of you did make some algebra mistake cleaning up. Okay, the ADT we don't know, so we'll leave that alone. Plugging in now. Step 4. Okay, pi to, what's R? 3. And dRdt? 3/4. Okay, calculator, here we go. All we have to do is plug that in, and you can leave it in terms of pi, but you don't really need to, so I'm just going to go ahead and put my pi in there. Times 2 times 3 times 3/4. Okay. 14.137. All right. Now, on word problems, you have to make sure that, so this was step 5, solving. Oh, yeah, that's what we're talking about. I didn't finish my sentence. We got to make sure that that makes sense, and we have a unit on it. So it's a rate of area, so it's going to be feet squared per time frame, which is second. Okay, now let's think about what that means. Okay, because if you understand it, it'll stick a little better. But so 14 feet per second. That's pretty large. Okay, the area is changing when the radius is 3. So I mean, 3 feet is a pretty big circle, right? Everybody do that? Try to skip the rocks, and they do that. Okay, this was a golf ball, but 3 feet is a huge concentric circle. Like it's from here to here.
Wouldn't it be 6?
Yes.
So 2 yards.
Yes. So that's huge. So your area is changing at 14 feet per second at the time when we get to the radius equals 3. That's what that means. Okay? So that's about as easy as you can get. 1 and 2 kind of have to start together because you have to figure out what equation you need and what variables you need, and then you can start identifying them. But when you're reading, underline the numbers, and then you know this information. Let's try another one, shall we? This one's not too hard either. All right, I keep scooting my thing over just so we can. All right, you got a ladder. You got a ladder. Begin sliding away from the base of the house at a constant rate of 2 feet per second. Okay, we have a 25-foot ladder. At what rate was the top of the ladder moving toward the ground when the base was 17 feet away from the house? So you can picture this. Sure, that's still here. All right, what is my picture? It's a triangle, a right triangle, where I have a 10-foot ladder. I can go ahead and put the 10 because that ladder is not going to change. Wait, let's see, 25. Oh, sorry, thank you. Wow. That is going to change to 25, but it's going to stay 25. Okay, so let's identify the variables. Because here's your ladder. If you move it and you're like, oh wait, that ladder is now bumped down, I'm sliding it this way. That's really bad. But anyway, then we have a new thing. So that's changing. So the bottom and the top would change, correct? Okay, so what are you going to call the bottom and the wall there?
I would call it bottom DB.
No, you wouldn't.
Oh, wait. No,
I'm going to call it B. Okay. All right, and what would you call the wall? Okay, sounds good. Okay, that is totally your choice. You don't like B because B's look like sixes. You use X and Y, whatever you want to use, but that's your total choice. Okay, now, don't say it out loud because of that. The hard part is like, wait, what is the relationship between A, B, and 25? All right. Shh. I did.
That's what I did earlier. Just smack me in the face with
You already did that.
Oh, yeah.
All right, so what's the relationship between this? That's it, Emma. Pythagorean theorem. Okay, I know you heard Emma, and I totally ignored her. She said, she said something about putting that 17 on there. I don't want to put the 17 on here because the 17 is just at that one moment. If it's changing, you want to have a variable on the side, okay? So this is, I already did step 2. What's step 1? What do we know here? What do we know about, let's see, what's the rate of 2 feet per second? Which one is that, dA dt or dB dt? Sliding away from the base, I would say. Is it getting bigger? Yes, when you're taking this and you're sliding, B is getting bigger, so dB dt should be positive. Sometimes it's messy. They tell you it's sliding away and it's getting smaller, then you have to make it negative. They're not going to tell you it never is negative. You just have to infer that from the information. Okay, at what rate is the top of the ladder moving? So what are we looking for?
We're looking for
dA dt equals what? When? What? Base was 17 feet. B equals 17. Okay. Now please put that information with your problem. Okay? I know you all are not used to doing that anymore. Remember, when you started out when you started word problems, you had to identify your variables, and you kind of got away from that, didn't you? But please do that. This is very important because if not, we're going to have to start doing that anyway. All right, so 1 and 2 are done. 3 steps, differentiate. Okay, so here we go. Differentiate each side. Step 3. Okay? So, Kathleen, tell me what the derivative of a squared is. Okay. And the derivative of b squared, Emily?
2b.
Good job. And the derivative of 25 squared, Christine? 0. You would believe how many people do 2 times, 25. And then it's like, wait, that's a constant. Doesn't matter if it's squared or not. Okay, so that's your step 3 to differentiate. Now we're ready to plug in the values. All right, A is, we don't know A. What's dA dt? We don't know. That's one you don't know, okay? What's B? 17, and what's dB dt? 2. Okay, I bet we can find A at that moment, because if this is 17, that's right, and this is 25, at the moment, A is what? Let's see. These here. 25, 17, and A. It's not pretty, I don't think. Square root of what? 336 or something like that? Okay. All right. It's okay to do the decimal, just don't round too much because that'll, okay. Now do algebra and solve. That was step 4. And 5 is solving. What? And if you're uncomfortable with this radical, totally, use the thing, you're totally fine. Just don't round too much. Okay, what did we get? What did you get, Hannah?
I know it's negative 34 over 4 radicals.
Okay, what is that? Can you give me a better number?
Well, like the original number that I had was negative 68 over 2 radicals of 36.
Okay.
I will find the decimal for you.
What do you got?
855.
Okay, that sounds good. If you got all those ugly decimals, radicals, just take it all the way down to a decimal round at the end. That's what you should get, -1 at 855. Wait a minute, why is that negative?
Because it's getting smaller.
Right, because A, as this slides down, A is getting smaller, so it should be you're decreasing that rate. Your rate is decreasing. Okay, did anybody not get that? You get it here? Okay, all right. Now, what that means is, at that moment where A is radical 336 and B is 17, the A is changing at that rate. I haven't talked about this yet. It hasn't come up. It sort of did, but plugging in the known values for the variables before finding the derivative will give you a very wrong answer. Okay? That's like that last problem when we may have wanted to plug in 17. Remember, they're all going to be numbers eventually. What's the derivative of a number? Well, that's just dumb. Okay? So you got to find the derivative first, then plug in. Okay? All right. Any questions on that one? So guarantee there'll be one like this on the test because that's pretty common. Let's try this one. Okay. The biggest deal for these are finding the relationship and figuring out your variables. The rest of it really will be easy. Okay. So you got this hot air balloon that is rising straight up. Okay. From a level field that is tracked by a rangefinder 500 feet from the liftoff point. So I'm lifting off. Where's the rangefinder? Where would you put them? Down here. Very good. So let's say the rangefinder is right here, and this is 500 from that point. Good job. So that's key. All right. At the moment, the rangefinder's angle of elevation, you've seen them on the side of the road. They're measuring. They have an angle that they're looking at. Okay. At that moment is pi over 4. The angle, so we have an angle here, so we probably have a right triangle there, is increasing at the rate of 0.14 radians per minute. That's an angle thing. So what are you going to call this angle? You call it whatever you want. R. Okay. All right. So that angle in there is R. All right. So what is 0.114? dRdt because it's a rate. Yeah, you can do theta if you want to do theta. You can do whatever you want. You don't like the R, maybe?
I'm used to angles.
I hear it. I hear it.
No, it's R.
Yeah. But they're all rates. So that's probably not a rangefinder angle. All right. Okay. We're going to call it theta. Theta, theta. All right. They're all rates, so if that's what you were calling R, that's probably not a good word, because they're all going to be rates. All right, how fast is the balloon? That's a rate. How fast is the balloon rising? So what other variable do we need here? The diagonal or the vertical? The vertical. That's how fast. That's okay. So that's changing as that balloon goes up and down, right? What do you want to call it for a variable? H. Okay. So dH dt is what we're looking for. When did we say we were talking about this? When what is pi over 4? Theta. Okay. So this is step 1. This is goes with step 1. Okay. What about 2? We need a relationship, Emma. Don't say it out loud. What is the relationship between theta, H, and 500? Theta, H, and 500. That diagonal is not even a problem.
Tangent of theta equals A over 500.
Nice. Okay, tangent is opposite over adjacent. Who knew tangent? Who's thinking already tangent? Good job. Okay, so those trig functions are going to come up. All right, now I'm ready to differentiate. This is step 2. But you might want to do something with that 500 before you differentiate. You have a question?
Okay, but you were playing those games.
We're recording. So, you're going to solve this. You're ready to differentiate. You want to do anything with that 500 before we differentiate? Is it easier? Yeah. Let's do it. All right. So 500 tangent theta equals H. Now we're ready to differentiate.
Is this something great?
Yes.
I don't like this because you don't know when the next step starts.
Well, you're just going to solve. Okay. So what's the derivative of tangent theta? Secant squared theta, and then we just multiply it by 500. Remember, that's the constant multiple rule. Okay?
I always end up doing
Yes, Catherine, we do d theta dt. Because it's implicit, whenever we're not doing time, we have to do. All right, and H dt. You can do one dt if that makes you. Okay, now what are we going to do?
We're gonna
Plug in. Okay. So what do we know? Theta is pi over 4, so there it goes. Okay, and d theta dt is what we're looking for, right?
We're sorry, yeah.
Wait. D theta dt is.
No, yeah, it's d theta dt.
Alright. Okay. Forgive me.
I won't. Just this time.
It's better over there anyway, because then you don't have to
It's
do.
0.14.
Well, thank you. Okay.
Oh, Jesus.
You don't have to call me that. All right. Now, pi over 4 over here. Pi over 4. What is the order pair? Radical 2 over 2. Radical 2 over 2. Cosine is the first one, and then we're going to flip it around, and because that's secant, right? And then we're going to square. Okay? You take, this is, remember, secant pi over 4 squared. Okay? Throw it in your calculator, you're good. You don't want to throw that on your calculator, that would be 4 over 2, right? 2. 1,000. So I got 140. Okay. All right, what's my, that is dH dt. So what is that? Units wise. Something per,
We lost the d theta dt.
it's right down there. Up there.
Okay, I get it.
All right, so we are looking at feet per minute, then, right? H is changing by feet per minute. Okay?
Parentheses, like, slash.
Do what? All right, any questions about that? So that's, let's see what's the next one, we may or may not. Yeah, I don't want to do that one yet. Okay, we'll do that one next time, because those get pretty weird.